Gazing at the night sky often leaves a strange impression. The silence among the stars seems almost tangible. You look up and see thousands, millions of points of light, and at some point, an intuitive thought, almost an instinct, dawns somewhere out there. Someone must be looking back. Our brain, accustomed to searching for faces in a crowd and movement in the grass, tells us we can't be alone. It seems impossible that among this endless scattering of light, there aren't other intelligent beings. But the problem is, our senses weren't designed to understand the cosmos. They evolved millions of years ago to help our ancestors survive on the African savanna. Intuition works great when you need to know where to run if you hear a twig snap, or how to catch a flying ball. But when we try to apply those same instincts to the scale of the universe, they break down. They simply weren't designed for such numbers and such distances. When people begin to look at space, not through the prism of fantasy and movies, but through cold mathematics and physics, a disturbing question arises. Why did we ever think our intuition had any right to judge the laws of nature? On Earth, everything seems simple. If you want to get somewhere, you walk. If you need to go faster, you accelerate. A car goes faster if you press harder on the gas. A plane flies faster thanks to a more powerful engine. But beyond Earth, the rules change. There, the familiar logic of everyday life doesn't exist. Their laws operate that don't take our desires into account and don't adapt to our expectations. And if you look at them closely, it becomes clear that the universe has erected several nearly insurmountable walls before civilizations. These walls aren't just obstacles. They are fundamental limitations. And they may explain the strange silence of space, the very silence that has troubled humanity for decades. We look to the sky and ask, where is everyone? But perhaps the answer is far simpler and, at the same time, more brutal. Maybe no one comes not because there is no one. Maybe no one comes because it is almost impossible to come. To understand this, we need to set aside the romanticism of science fiction and look at reality. And the first thing that shatters our notions of space is distance. We pronounce the word space as if it simply denotes the empty space between planets. But in reality, it's a scale the human brain is almost incapable of comprehending. Our perception of distance was shaped in a world where the greatest distances are a walk or a flight across an ocean. We can imagine driving from one city to another. Perhaps we can imagine flying halfway across the planet. But that's where our imagination ends. Let's start with the simplest level of scale, Earth. It's our home, our world. Its diameter is about 12,700 kilometers. For humans, this is an enormous size. We build airplanes to fly around it, and it takes almost 2 days. But on the scale of the universe, Earth is a tiny speck of dust, a small rock orbiting an ordinary star. The next step is the distance to the Sun. It's approximately 150 million kilometers. This number is already beginning to exceed the limits of ordinary experience. But even this can be put into perspective. Light, the fastest moving light in the universe, travels this distance in approximately 8 minutes. This means that if the Sun suddenly disappeared, we would continue to see its light for another 8 minutes. Daylight on Earth would last another 8 minutes before absolute darkness descended. At this stage, reason still holds. We can still relate distance to familiar concepts, but beyond that, the real abyss begins. The next step is the nearest star after the Sun. It's called Proxima Centauri, and it's about 4.5 light years away. The number 4 seems small. 4 years isn't that long, but the word light year changes everything. A light year is the distance light travels in 1 year, and light travels at about 300,000 kilometers per second. Every second. To get a sense of scale, consider the fastest object ever built by humanity, the Parker Solar Probe. It accelerates to nearly 700,000 kilometers per hour. That's so fast that if it were to orbit the Earth, it could circle the planet in just a few minutes. If such a spacecraft were to fly in a straight line from New York to Tokyo, it would take less than a minute. Now imagine you boarded this spacecraft and headed to Proxima Centauri. How long would the journey take? A month? A year? 10 years? No. At the fastest speed humanity has ever achieved, the journey would take approximately 6,600 years. This is the nearest star, our cosmic neighbor. If you had gone there when the Egyptian pyramids were being built, you would only now be beginning to reach your destination. The entire history of civilization would have been covered in a single journey, but that's just the beginning of the scale. Because beyond that, the galaxy begins. Our home in space is the Milky Way. It's a gigantic system of hundreds of billions of stars. Its diameter is approximately 100,000 light years. If you tried to cross it at the speed of Parker's solar probe, the journey would take hundreds of millions of years. That's longer than most species on Earth have existed. In that time, evolution could completely transform the travelers. They could transform into a completely different life form before they even reached the halfway point. And here the first realization emerges. Space isn't just vast. It's practically infinite by human standards. Even immediate goals require a time span that exceeds the history of civilization. But many people at this stage say, okay, the distance is huge, but technology is advancing. People used to think it was impossible to break the speed of sound. Then jet planes came along, and it became a reality. So, one day we'll simply create more powerful engines and fly faster. And here the second verdict of the universe appears, the speed of light. The speed of light is approximately 300,000 kilometers per second. But the important thing about it isn't the number. What matters is its significance for the very fabric of reality. The speed of light isn't just a technological limitation. It's a fundamental limit to how quickly information and causal relationships can propagate throughout the universe. While on Earth we're accustomed to linear logic, more effort yields more speed. At cosmic speeds, everything changes. As an object accelerates and approaches the speed of light, energy begins to behave strangely. The faster the object moves, the more energy is required for further acceleration. But this increase in energy becomes increasingly rapid. At some point, the added energy no longer significantly increases velocity. It begins to manifest itself as an increase in effective mass. The object becomes heavier from the perspective of relativistic physics. And the closer the speed to the speed of light, the stronger this effect. To accelerate an object with mass to the speed of light itself requires an infinite amount of energy. Not just an enormous amount. Infinite. This means that no technology can surpass this limit. It's possible to get close. It's possible to reach 90% of the speed of light. 99. Perhaps even 99 and many nines after the decimal point. But reaching the speed of light itself is impossible for any object with mass. This is not an engineering problem. It is a law of nature. And this is where the dream of fast space travel begins to crumble. Because even if a civilization is incredibly advanced, it still lives in the same universe and obeys the same laws of physics. And if these laws say that the speed of light is the limit, then it is the limit for everyone. And when people begin to understand this, space begins to look different. Not like an open road between the stars, but like an ocean with incredible distances and strict speed limits. But even if we accept this limit and say, okay, we won't fly at the speed of light, we'll fly slower, the next question arises. And it brings us to another harsh reality of the universe. I'll pick up where we left off. We've already established that space is incredibly vast, and that the speed of light sets an absolute limit for any object with mass. But even if a civilization accepts this limit and says, okay, we'll travel slower, say at 10% the speed of light, another problem arises. And this problem destroys the dream of interstellar travel even faster than distance or speed limits. This problem is called energy. When people think of space travel, they often imagine a spacecraft similar to an airplane. There's a hull, an engine, and fuel. We're accustomed to the idea that more fuel and a more powerful engine mean we can fly further and faster. But in space, things are much more complicated. At the very beginning of the 20th century, Russian scientist Konstantin Tsiolkovsky wrote down an equation that is now known as the Tsiolkovsky rocket equation. It seems simple, almost boring, but in fact, it's one of the most ruthless equations in physics. The gist of this equation is that a rocket moves by ejecting mass. Fuel is ejected backward, and thanks to the law of conservation of momentum, the ship moves forward. But this creates a vicious circle. To accelerate a ship, you need fuel, but fuel has mass. And to accelerate that fuel, you also need fuel. And that extra fuel also has mass. And to accelerate it, you need even more fuel. It's an exponential chain. The faster you want to go, the more fuel you need, and the more fuel you take on, the heavier the ship becomes. And the more fuel is needed to accelerate all that mass. This makes space travel a nightmare for engineers. On Earth, you can build a car and simply refuel it along the way. But in space, there are no refueling stations between the stars. You have to carry all the fuel with you from the start. And this leads to astonishing results when you start doing real calculations. Let's imagine a simple scenario. Let's say you want to send a small spacecraft to the nearest star and do it within a human lifetime. Let's say that's about 40 years. To make it in that time, the ship would have to accelerate to a significant fraction of the speed of light. But here comes a detail that many people forget. Once you reach your destination, you need to stop. If you simply accelerate and fly to another star at incredible speed, you'll miss it like a bullet. So the ship must not only accelerate, but also decelerate. And that means braking fuel must also be carried along for the entire journey. When engineers plug real numbers into the rocket equation, the results become almost absurd. Using modern chemical rockets, the amount of fuel needed to accelerate one person to the nearest star and then decelerate would exceed the mass of the entire observable universe. It sounds like a joke, but it's not. It's a direct consequence of the mathematical formula. You might say, okay, chemical rockets are a primitive technology. Let's imagine a more advanced one. For example, nuclear fusion. Scientists hope to one day create reactors that can use hydrogen fusion in the same way the sun does. Such an engine would be much more efficient. But even then, Calculations show that an interstellar ship would have to be almost entirely filled with fuel. Imagine a huge cylinder the size of a skyscraper, 99% fuel, and only 1% payload. And this entire colossal structure is needed just to deliver a small spacecraft or crew to a neighboring star. Then comes the next idea. What if we used the most powerful fuel in the universe? Antimatter. When a particle of matter collides with an antiparticle, their entire mass is converted into energy. This is the most efficient reaction known. A single gram of antimatter can release energy comparable to a powerful explosion. It seems like the ideal fuel for space travel. But here another problem arises. Antimatter is incredibly rare. In laboratories, scientists can only create it one atom at a time in particle accelerators. And producing even microscopic quantities requires enormous resources. The cost of a few nanograms of antimatter is estimated at billions of dollars. To accumulate enough antimatter for an interstellar spacecraft, humanity would have to use the entire energy capacity of the planet for millions of years. And even if some civilization reaches an incredible level of development and manages to build a Dyson sphere around its star, collecting virtually all of its energy, the question of efficiency remains. Intelligent civilizations likely know how to count. They understand the value of energy. And when faced with the task of sending a ship tens of thousands of light years to a random planet, they might ask a simple question: why? Why waste a star's energy on a journey to a distant world that might turn out to be empty, when the same energy could be used at home to create virtual worlds, giant orbital cities, or incredible technologies? The more advanced a civilization becomes, the more it values efficiency. And interstellar travel is perhaps the most inefficient use of energy imaginable. But let's imagine that a civilization decides to send a ship anyway. Perhaps they're curious. Perhaps they have a scientific mission. Perhaps they just want to explore the galaxy. They overcome the energy problem, build a ship, and launch it into space. Then comes the next wall, the next problem, the one that people who watch space movies rarely think about. This problem is called biology. The human body is an amazingly complex system, but also a very fragile one. It evolved in very specific conditions: Earth's gravity, magnetic field, dense atmosphere, and protection from cosmic radiation. All of this creates a safe shell around our planet. But step outside of this shell, and the environment becomes extremely hostile. Beyond Earth's magnetic field, space is filled with high energy particles. Cosmic rays aren't just light. They're protons and heavy atomic nuclei moving nearly at the speed of light. When such a particle passes through the human body, it damages cells and breaks DNA molecules. To the body, these are like tiny bullets flying through tissue. Even a trip to Mars poses a serious challenge. Astronauts receive significant radiation exposure during the journey, increasing their risk of developing cancer. But a trip to another star lasts not years, but centuries or millennia. Over that time, the radiation would destroy any biological organism. We could try to protect ourselves with thick shields made of water, lead, or other materials. But the mass problem arises again. The thicker the shield, the heavier the ship. The heavier the ship, the more fuel is needed to accelerate it. And we're back to the rocket equation, back to the same closed loop. But radiation isn't the only biological problem. There's also gravity. The human body is accustomed to living under Earth's gravity. When astronauts spend several months on the International Space Station, Astonishing changes occur. Bones begin to lose density. Muscles atrophy. The heart weakens because it no longer has to pump blood against gravity. Even the eyes can change shape, impairing vision. Now imagine a journey lasting hundreds of years. An organism deprived of normal gravity gradually deteriorates. Perhaps a rotating ship could be created to artificially create gravity. But that would further complicate the design. Some people are proposing the idea of cryosleep. It would be possible to freeze a person, send them into space, and wake them up many years later. But this poses a biological problem. When water inside cells freezes, ice crystals form. These crystals rupture cell membranes. After thawing, the cells are destroyed. Modern science cannot freeze complex organisms without causing serious damage. There's another idea: generational ships. People live on such a ship, have children, grow old, and die, while their descendants continue the journey. After many generations, the ship reaches its destination. But this raises a social problem. Imagine several hundred people living in a metal cylinder for 500 or 1,000 years. Their culture will begin to change. Their language will change. Conflicts will arise. The social structure may collapse. Perhaps, after a few generations, people will completely forget why their ancestors set out on their journey. Even if they remember their destination, genetic problems can accumulate. A limited population leads to inbreeding and an increase in genetic defects. After hundreds of years, the crew may be too weakened to survive on a new planet. This is why biology becomes another serious wall between the stars. But one might object fine, perhaps biological beings are incapable of such travel. But what if civilizations create machines? Robots or artificial intelligence that can survive cosmic distances. This sounds more realistic. Machines don't get cancer. They don't require an oxygen atmosphere. But even here, the problems don't disappear entirely. Electronics are also vulnerable to radiation. High-energy particles can alter the state of transistors and cause errors in computer memory. These are called bit flips. Over time, such damage can accumulate. Moreover, materials age, metals tire, micrometeorites constantly bombard the ship. Even a dust particle traveling at tens of kilometers per second can penetrate the hull like a bullet. Over thousands of years, the risk of damage becomes very high. And here it becomes clear that even machines have a limited lifespan. And the galaxy is too vast for any warranty period. And all this brings us to another, perhaps the strangest problem, the problem of time and information. We have reached the final barrier, perhaps the most silent and at the same time the most destructive to the dream of a meeting of civilizations. Even if we imagine that an intelligent civilization has somehow overcome distance, solved the energy problem, found a way to protect biology, or replace it with machines, one fundamental reality of the universe still remains. This reality is related to time and information. The universe is a very poor communication system. We often imagine space as a vast expanse where you can send a signal and sooner or later someone will hear it. But in practice, things are much more complicated. Humanity began actively using radio about 100 years ago. This means that our radio signals have been traveling from Earth in all directions at the speed of light for about a century. As a result, a kind of radio signal bubble has formed around our planet, approximately 200 light years in diameter. 200 light years sounds impressive. But when compared to the size of our galaxy, it becomes clear how insignificant it is. The Milky Way's diameter is about 100,000 light years. This means our radio bubble is a tiny dot within the galaxy's gigantic disk. On a galactic scale, humanity has barely begun to speak. For someone to hear us, many conditions must be met. First, somewhere within this radio bubble, there must be a civilization with instruments sensitive enough to detect the faint signals. Second, their radio telescope must be pointed precisely toward Earth. Third, they must be listening on the exact frequency the signal is being transmitted on. And finally, all of this must happen at the right time. There's a so-called cosmic needle in a haystack problem in space. There are billions of stars. There are billions of possible frequencies. There are an infinite number of moments in time when a signal can be sent or received. The probability that two civilizations will accidentally end up on the same frequency, facing the same direction, and at the same time is extremely small. Imagine an alien civilization pointed its radio telescope at Earth in the year 1500. They would hear absolute silence because humanity hadn't yet invented radio. Now imagine the opposite situation. They're listening today, but they're 500 light years away. Our radio signals simply haven't reached them yet. To them, Earth still looks the same as it did 500 years ago. And here an even deeper problem appears: the asynchrony of civilizations. Civilizations don't last forever. They emerge, develop, reach technological levels, and then can disappear. Perhaps due to environmental disasters, wars, asteroids, or simply internal changes. Humanity has existed as a technological civilization for only about 200 years. Even if we're lucky enough to survive another 10,000 years, it will be a mere blink of an eye on the scale of the universe. The universe is approximately 8 billion years old. In such a vast ocean of time, the probability of two civilizations colliding not only in space but also in time is extremely small. It's like two fireflies in a vast forest. One lights up on Tuesday night, the other on Friday. They both shine, but they never see each other. Perhaps an intelligent civilization existed on a planet near Proxima Centauri 1 billion years ago. They might have built cities, developed technologies, and gazed at their night sky with the same questions. But 1 billion years is a vast span of time. Their star could have changed. Their planet could have become uninhabitable, or their civilization could have vanished long before humanity emerged. It's equally possible that in 1 billion years, a new civilization will emerge on some planet orbiting another star. It will ask the same questions, look at the stars and search for signals. But by then, Earth may already be a long, dead world. That's why the silence of space may not be a sign of emptiness, but rather a sign that civilizations exist in different eras. They arrive at the cosmic party at different points in time and simply don't intersect. When you combine all these factors, the incredible distances, the speed of light, the colossal energy costs, biological limitations, and the asynchrony of time, a rather stark conclusion emerges. Even if intelligent life is widespread throughout the universe, encounters between civilizations may be nearly impossible. And here comes another question that people often ask. If aliens can't visit because of all these restrictions, how then can we explain the reports of unidentified flying objects? In recent years, several videos from military aircraft have emerged showing strange objects moving in unusual ways. These videos are highly controversial. Some believe they are evidence of the presence of alien technology. But if we apply the physics we've discussed, serious problems with this explanation arise. For example, some of these objects, according to observers, accelerate from zero to enormous speeds almost instantly. Such acceleration would represent thousands or even tens of thousands of g-forces. At such g-forces, any known material begins to deteriorate. Electronics cease to function, and a biological pilot would literally be liquefied. Furthermore, an object moving through the atmosphere at hypersonic speed should create a powerful shock wave and a bright plasma trail. The air around it heats up to thousands of degrees. This is the physics we observe when meteorites enter the atmosphere. But most of these videos show nothing of the sort. We see only a blurry spot on the infrared camera. Therefore, it's far more likely that many such sightings can be explained by simpler factors, camera optical effects, lens flare, drones, birds, or image processing quirks. This doesn't mean all the mysteries have been explained, but it does mean that extraordinary claims require extraordinary evidence. Blurry video footage isn't such evidence. But despite all this, the story doesn't end in pessimism. Because when we remove the fantasy that aliens will one day arrive and solve our problems, we begin to see the universe differently. The silence of space forces us to mature as a species. It reminds us that no one will come to save us from our own mistakes. No one will solve the problems of climate, war, or economics for us. We live on a small blue planet, which is the only home we have. But there is also a surprising beauty in this isolation. If the galaxy were filled with spaceships, as in science fiction, Earth would be just another stop on the interstellar highway. But in a quiet universe, life becomes something incredibly rare and precious. Our planet becomes a true cosmic oasis. Every carbon atom in our bodies was created inside dying stars billions of years ago. We are literally made of stardust. The universe underwent billions of years of evolution to finally produce beings capable of questioning their origins. In this sense, humanity is a universe that has learned to look at itself. And while we may never shake hands with an alien or meet them in a space bar somewhere on the edge of the galaxy, we still keep searching. Scientists listen to the cosmos with massive radio telescopes. They're looking for so-called technosignatures, traces of technologies that advanced civilizations might be creating. These could be unusual radiation, laser pulses, or the heat signatures of gigantic energy facilities. The search continues. But now it's being conducted not with naive hope, but with patience and a scientific approach. And the next time you look up at the night sky and feel that strange silence, don't perceive it as loneliness. Think of it as an invitation. The universe doesn't have to give us answers. But that's precisely why searching for those answers makes our existence so wondrous. We are here. We understand more and more. And perhaps this is the most important miracle of all.